Okay, in this lecture, we're going to talk about colligative properties. And these are properties that depend not on the exact identity of the solute, but just how much of said solute there is in a solution. So if you're confused about what a solution is and its components, you can go back and watch some of the previous lectures. But a solution is really at least two things: a solvent in greater quantity and a solute in less quantity, mixed together homogeneously. So colligative actually comes from the word colligatus, which is Latin and means bound together. So this word right here essentially means bound together in Latin. And what's unique about these properties, most properties in science, and chemistry in particular, really depend on the exact thing that you're mixing together. So it would depend if it's sodium chloride versus potassium fluoride versus calcium carbonate. But these properties we're going to talk about today don't depend on the identity, only the quantity. And that's what makes them colligative. So if you have a beaker of water, right, and there's a certain vapor pressure of this water, well, if you dump sodium chloride in and it makes this, or you're dumping, lithium bromide in and it makes this, it doesn't really matter if it's lithium bromide or sodium chloride. All that matters is exactly how many ions I'm introducing to this water to describe how the vapor pressure or the boiling point or the freezing point or the osmotic pressure changes. So in today's lecture, we're going to define each of these things. We've already talked about a couple in previous lectures, and then we're going to introduce the formulas in order to quantify how much they change for the given quantity of solute. So again, it depends how much solute you're putting in, not exactly the identity of said solute. Okay. So the first one we're going to talk about is vapor pressure. And vapor pressure we've talked a lot about in previous lectures. And vapor pressure is the result of a dynamic equilibrium. And again, equilibrium, a lot of students think means nothing is happening. But a dynamic equilibrium means there is a lot happening. It's just equal and opposite, such that overall there's an equilibrium. So in vapor pressure, the dynamic equilibrium is that some of these solvent molecules here have enough energy from the Maxwell-Boltzmann distribution of energies to overcome their intermolecular forces here and break each of those attractions and go up into the gas phase. So every snapshot in time, there's some number of molecules up here in the gas phase, which were delivered there from the solution phase just because they had enough energy, right? But eventually those bounce back and return to the solution. But again, those things are happening when there's an equal amount leaving as there is entering. Well, then there's a total number of molecules up here for any given snapshot in time. Here there's 5. 1, 2, 3, 4, 5. And so the vapor pressure here would be 5, even though these 5 molecules might quickly return down to the solution phase. Well, by the time they do, there's another 5 that have wound up in the gas phase. So that's the sense of dynamic equilibrium. Now, part of the property that determines what the vapor pressure is the nature of these interactions between the solvent molecules. Now, in a solution, you're putting in some solute. So instead, if these spheres are representing water, imagine these smaller green spheres representing, say, sodium or chlorine ions. And what's particularly going to be the focus for today's lecture is that these are non-volatile. So we're looking at the vapor pressure, but the vapor pressure comes from the molecules that are the solvent. The solute molecules, okay, pictured in the squares here, these darker green spheres, will not be able to leave. They're non-volatile. Okay, so the colligative property of vapor pressure here depends just how many of these non-volatile things there are, not their identity. And it's really just a sort of physical phenomenon that these solute particles really get in the way of this surface level. Now, vapor pressure is determined by this dynamic equilibrium of these solvent molecules going up into the gas phase. So it makes sense if I put some solute in the way that blocks this one from reaching the surface, then it can't enter the gas phase. It's blocked at the surface by this molecule, this solute molecule that is non-volatile anyways and isn't going up to the gas phase. So this solute blocks the solvent from escaping into the gas phase, hence the pressure above, the vapor pressure, in the solution will always be less than the pressure of the pure solvent. Said another way, if I don't have any of these dark spheres, the solute molecules here, there's some amount of solvent molecules in the gas phase, and those gases exert a pressure on the sides of the container. That is the vapor pressure, the pure solvent. But once I pour some solute in, now I have a solution. Now some of the sites are blocked from the molecules going up into the vapor phase, and so the overall pressure will be less because there will be less gas molecules up here, 3 as opposed to 5 before. And so the vapor pressure drops. Okay, so all that is sort of assumed at a certain temperature. Obviously, if you change the temperature, you're changing the energy of the molecules down here, and they might have more or less energy to increase their prevalence in the gas phase, overcoming all these, if it's water, hydrogen bonding networks, or whatever intermolecular forces there are. So that's conceptually our understanding of vapor pressure and why it lowers when you add in a solute. Now, the exact law that describes this is known as Raoult's law. Okay, it's not Raoult, it's Raoult. And Raoult was the first to quantify this by studying a lot of non-electrolyte solute mixed with solvents. And the vapor pressure of this solution, as we said before, right, will be lower than the pure solvent. But here it's quantified by this mole fraction here. Okay, and this is the mole fraction of the solvent. A lot of students will mess up and make it of the solute when they go and calculate it. So put a star in your notes or something, or just commit to memory that this is the mole fraction of the solvent, right? So it's probably going to be something like 0.9 or 0.8 or, right, 0.99. It's always going to be a number that is quite close to 1, right? It definitely has to be above 0.5. Well, I guess not if there's multiple solutes, but most of the time it'll be above 0.5 because it's the solvent. It's what is the majority of the solution. Okay, so you can have that conceptual check when you do some of these problems. So the vapor pressure of the solution above, once I mix in some solute, is going to be lower than the pure solvent. So this right here, this notation is the pressure, and in this case, the vapor pressure of the pure solvent. Now, the pressure of the solution will always be less than the vapor pressure of the pure solvent because this mole fraction here is always less than 1. It's a fraction, right? It's the amount of solvent in moles divided by total moles, right? I could probably write that here, the actual formula, right? This mole fraction of the solvent is going to be equal to the moles of solvent over moles of solvent plus moles of solute. It's just a fraction. And that'll always be less than 1. Okay, so this is how we quantify it. This is known as Raoult's law. Let's see it in action. So here's a practice problem for you to actually calculate something related to Raoult's law. Please pause the video here and try to work through it yourself. Struggle, fail, that's okay. You can get it wrong. This is the practice. This is where you learn how to do it. So please pause the video here and try for yourself. Otherwise, I'm going to go forward and solve it for you. Okay, so what mass of C3H8O2 is added to 0.34 kilograms of water to reduce the vapor pressure by 2.88 torr at this temperature? The vapor pressure of pure water at this temperature is 55.3 torr. So obviously we just talked about Raoult's law. That's what we're using here. But remember, in the future, in an exam, in your daily life, if you're trying to figure out something like this, you're not going to automatically think of Raoult's law until you read through the question and see that it's a vapor pressure problem, but it's for a solution. Okay, so you need to realize that when you see these vapor pressure, those words, and solution, you should definitely be thinking Raoult. That's a no for Raoult's law. Right? And Raoult's law again says that the pressure of the solution, the vapor pressure, is the mole fraction of the solvent times the pure pressure of the solvent. Okay, so let's go through and read the question again now that we've identified the formula to use, and really take note of all the numbers here. So this is my solute. Maybe I'll outline that in red. And I know that for a number of reasons, but primarily because water's usually going to be the solvent. What else do I have here? I have the fact that the vapor pressure of pure water is 55.3 torr, so that seems important, but that is my pure solvent vapor pressure, so I know I'm putting that in right here. I'm also told that when I add this solute to the solvent, the vapor pressure reduces by 2.88. So the vapor pressure of the solution, you might be poised to write 2.88. Okay, but that's wrong. That's how much it's lowered by, right? The lowering will be pretty reasonable. It's not going to drop from 55 to 2. Okay, the pressure of the solution is here 55.3 minus 2.88. It dropped by that much. So 55.3 minus 2.88, I believe, gives us 52.42. And that is my pressure of the solution here. So now I have the formula that this is the pressure of the solution, the pressure of the solvent I have right here, and all I need to solve for is chi of the solvent. That is the mole ratio of the solvent. I can divide both of these things out. And you might be thinking, well, aren't you going to plug in the mole fraction of the solvent? No, it turns out what the question is asking is the mass of the solute. And so it's clear that I need to take this massive solute, you should be able to see this by now, put it into moles, and then figure out the mole fraction by putting this into moles as well. So I can solve this Raoult's law for the mole fraction here. Divide both sides by 55.3 torr. The torrs will cancel. And the mole fraction of the solvent will equal 0.948. Now, this mole fraction we know is moles of solvent. This is where many students will mess up. It's solvent over moles of solvent plus moles of solute. Okay, so the green, the solvent, is going to go here and here, and the red, our solute, is going to go here. And that's ultimately what I'm trying to find, this moles of solute here. So let's plug in what we do know. And what we do know is the moles of solvent. This 0.348 or 0.340 kilograms of water is 340 grams of water. And I can divide that by the molar mass of water, 18.02 grams per mole. And I get a number of moles of water of 18.868 moles. Now I can plug that number in, both here and here, and solve for the result. Solve for my x here, which is my moles of solute. When I do that, I should get a moles of solute equal to 1.035 moles. This is the solute, C3H8O2. And just as a conceptual check here, this moles should be less than the moles of water, 18.868, because it's the solute and water's the solvent. There should be more, so that looks good. And the last thing I'm going to do is convert this to grams because, well, that's what it wants in this problem. What is the mass? Okay, so in 1 mole of this C3H8O2, you can add up the molar mass. It should be 76.11 grams per mole for a final answer of 78.8 grams of C3H8O2. Okay, so if you had to create a solution with a certain vapor pressure, and vapor pressure is important because it tells you something about the boiling point of the substance, which we'll get to later. But if you were asked to do that or wanted to do that, this is exactly how you would figure out how many grams you need to weigh out of C3H8O2 to add to your water to end up with this solution. Okay, so here's your final answer right here, 78.8 grams. So that is vapor pressure, one of the 4 colligative properties that we're talking about today. Remember, colligative properties are properties that depend just on the just on the quantity, not the identity. So again, it's just about the moles of the solute here, not exactly the forces that are involved. You could say, well, it depends on the identity because, you know, the mass is going to change due to the molar mass changing, but the colligative meaning it depends on the identity, not the identity, but the quantity, is it just depends on the moles. It doesn't matter if it's, you know, ionic or covalent and the type of intermolecular forces involved. That's what we're ignoring when we say it doesn't depend on the identity. 78.8 grams should be the answer. Now, the two kind of resulting properties that are affected here are boiling point elevation and freezing point depression. And we can go back and look at our phase diagrams, which we've covered in a previous lecture, to see why this is the case. Now, what you see here is a line that is moved. And you remember, we just changed the vapor pressure, okay? What we learned from this Raoult's law equation, right, is that the pressure of the solution always lowers. So when you add this solute into the solvent, the pressure above the solution drops. Well, on a phase diagram, this liquid gas separation line, this blue line right here, is in fact the vapor pressure. So at a given temperature, this line tells you what the vapor pressure is. So if I'm adding in a solute at every single temperature, doesn't matter what, that new solution will have a lower vapor pressure. So this whole curve moves down as a result. Again, because we're adding in a little bit of solute, that lowers the vapor pressure at all temperatures. That will happen. And so the entire line that separates liquid and gas phase, and over here is solid, that whole line shifts down. And now we can look at the boiling point. Where is the boiling point on here? Well, if my atmospheric pressure is here, right? Let's say this is happening at sea level, 1 atmosphere. The boiling point is, you walk over to the curve right here. That's what it used to be. And it would be right here. This would be the temperature of the boiling point. But now that the curve is moved, where does 1 atmosphere intersect the liquid gas interface? It is here. And this boiling point is higher. So this new TB prime, we'll call it, now that the curve has moved because we've added solute, leads to a shift in the boiling temperature. Okay, so for every, colligative property, vapor pressure, boiling point, elevation, freezing point, depression, it's all really a result of this vapor pressure effect. So the boiling point will go up. What about the freezing point? Okay, solid, liquid, gas. Now that I have moved this vapor pressure curve, there is still going to be a singular triple point. This triple point, right, has to exist where the vapor pressure curve meets up with this original curve. So the triple point is now here, which suggests that the green curve also moves, and it does, to here. So when I mix a solute in, the phase diagram of the solvent shifts. The green curve shifts to the left a little, the blue curve shifts down a little. The blue curve shifting down means a shift in the boiling point. The green curve shifting left means a change in the freezing point. So let's go back and look at this. Here is my 1 atmosphere pressure. I walk over, the solid liquid separation moves from here to here. Here's the original freezing point. Here's the new freezing point. And so the freezing point will always be depressed. The boiling point will always be elevated. All right. So this is why we add salt to the roads. It requires a much lower temperature for the water on the road to freeze and create icy conditions. All right, we're seeing that happen here because of this shifting of the solid liquid line on the phase diagram, which is only shifting because the liquid vapor phase diagram, liquid gas vapor curve is shifting down, and the triple point must be maintained. Okay. The long and short of it is the freezing point will get depressed always, the boiling point will be elevated. Now you can quantify exactly how much this happens with these formulas. And these are pretty straightforward, right? If you want to think about in a certain climate, how much salt do we have to add to the liquid water to depress the freezing point to a temperature that is, -3 degrees Celsius. Is that enough? -5 degrees Celsius, -8 degrees Celsius. How cold is your climate? What is a allowable freezing point for these things? You're going to need to calculate the freezing point depression with this formula shown right here. And there's 2 of them because it's boiling and freezing, but they're very, very similar. Obviously, the boiling point gets elevated, so there is a inherent plus here. The freezing point drops, so there's a negative here. So this change in temperature when you add salt to the water, right? So here's our glass of water, and we're adding some kind of salt. Again, it doesn't matter if it's sodium chloride or potassium iodide, anything that has the same number of particles will create the same effect. Okay, so I don't know what salt exactly they use to prevent freezing roads, but it doesn't really matter. Now, one thing that will matter is the Van Hoff factor. So one thing in the formula I want to point out right here is this lowercase I. That is the number of particles that this compound creates. So the quantity, remember, in colligative properties is important. It doesn't matter if it's sodium chloride, right, or potassium iodide, and those 2 things have the same Van Hoff factor. They break into 2 things, sodium plus and chlorine minus, or potassium plus and iodine minus. So these things would have a I of 2. Okay, something that's a non-electrolyte means it doesn't ionize. Something like sucrose would have a Van Hoff factor of 1. That's why we don't put sugar on the roads. Also because then kids would be trying to lick the sidewalk, as well as animals. That also would not be great. Non-electrolytes, I equals 1. You could have something like magnesium chloride, and this will separate into 3 particles, 2 chlorine ions, 1 magnesium ion. So the I Van Hoff factor, first winner of the Nobel Prize in Chemistry, by the way, Van Hoff. The Van Hoff factor here would be 3, the number of things it separates into once you put it in the solvent. So that's the Van Hoff factor. The constant here is going to be dependent on the solvent. For water, there's a certain Kb and Kf, and those are usually the ones we're concerned about. In a lot of chemistry, it's going to be aqueous, water involved. The last thing here is the molality. And we covered this in our last lecture. You can go back and watch that video. But this is a different unit of concentration than most people typically use. This molality here is not molarity, it's molality. And the molality has the following formula. Moles of solute over kilograms of solvent. Okay, so you have to know how much water you have here in kilograms. That's the bottom. And how many moles of solute in the top. Okay, so let's see this in action again, the application here is maybe you're a city planner and you know the certain climate and you know on average how cold your roads get. And so you need to figure out what kind of salt solutions you need to buy in order to ensure that your roads don't ice over very often. Well, you need to know the temperature required. That is the freezing point, the new freezing point of the solution. And that's what we're going to calculate here from this change in freezing point. So let's see this worked out. Here's a practice problem for freezing point depression and boiling point elevation. I'm going to work through it. If you're watching the video and would like to attempt yourself, please feel free to pause the video here. Okay, so let's go through and calculate this. And another sort of application here, antifreeze in our car contains ethylene glycol, a non-electrolyte, and water. As soon as I read that, non-electrolyte, alarm bells going off for Van Hoff, I equals 1. Calculate the boiling point and the freezing point of a 25% by mass solution. That's weird because I need molality. Not sure how that's going to work. Of ethylene glycol and water. For water, Kb equals this, Kf equals this. So let's think about our formula here for the new boiling point. Okay, it's antifreeze. I know we want to calculate that, but we're going to calculate both boiling point and freezing point. Let's do boiling point first. Delta Tb equals the Van Hoff factor I times the constant Kb times this molality. And this is straightforward because I is 1. In this example, it's a non-electrolyte. Kb, 0.510 degrees Celsius per molal, for molality, times the molality. So really I just have to multiply these three things together, but I don't have the molality. What I have is 25% by mass solution. In the same way, my freezing point depression, it's going to go down, so there's a negative sign, and there's still the I, 1. There's the freezing point constant, which is different than the boiling point. Right, so notice it's not 0.5, it's 1.86. Students will often make that mistake. And there we go. So if we can figure out the molality, we just plug this in and we have our answers. So how do I get molality? Well, what I notice here, what I'm given for the unit of concentration is 25%. In the last video, we did a lot of exercises converting between percent mass and molality or molarity or ppm or ppb or any of these units of concentration. So if you need help on that math, go back and watch that video. 25% mass solution. I'm not told how much total there is, so let's just assume there's 100 grams total. Okay? If there's 100 grams total, then 25% by mass means there's 25 grams of ethylene glycol divided by 100 grams total, which means 25 grams ethylene glycol. This, I suppose, should be eth gly plus 75 grams water. Okay, so let's assume that is my 25% by mass solution. You could choose 1,000 grams for the total. I chose 100 grams. It makes the math easy. So now how do I get molality? Well, the molality here, remember, is moles of solute divided by kilograms of solvent, where my solvent is H2O. So the denominator is easy because I have 75 grams. Well, I'm just going to put that in kilograms, move the decimal point 3 places. There we go. Done. Easy. There's my kilograms of water. The moles of solute is only slightly more difficult. I have to take this 25 grams of ethylene glycol and convert it to moles using the molar mass. The molar mass of ethylene glycol is, you can add it up from the periodic table there, but it looks like should be 62.068 grams, which means the moles here is 0.40278. I'm just keeping a lot of digits here because in the end I can round off to my sig figs. So now I have this ethylene glycol. I take this number, plug it in here, divide by 0.075, and I get an answer that is 5.37 molal. And now this 5.37 molal, should have organized this a bit better. My apologies. goes in here and here. So 1 times 0.5 times 5.37 will give me my final answer here in terms of the delta TB of 2.7 degrees Celsius. And down here, -1 times 1.86 times 5.37 gives me a number like -10.0 degrees Celsius. And notice that this boiling point elevates much less than the freezing point depresses. And that's a factor of these constants here, right? The freezing point constant is a lot greater, so the freezing point moves a lot more for water. For different solvents, these numbers will be different. So overall, calculate the boiling point and the freezing point. These aren't my final answer, right? If you say the new boiling point is 2.7, that's wrong. Because we know water boils at 100 degrees Celsius. So don't go writing down that water now boils at 2.7 degrees Celsius unless you can prove it and thus win a Nobel Prize. But that's probably not happening. Okay, the new boiling point for water is 100 plus this 2.7. And so the new boiling point is 102.7 degrees Celsius. That is my final answer for boiling point. The new freezing point, well, water conveniently freezes at 0 degrees Celsius. That's why Anders Celsius from Sweden chose his scale this way, because it's sensical, unlike certain other units of temperature that only certain countries use. Celsius is a good temperature scale, and the freezing point is -10 degrees Celsius minus 0, the original, so it's still -10 degrees Celsius. Okay, so there's my final boiling point and freezing point. Okay, so that's how you work out how much these freezing points get depressed or boiling points get elevated. And so the antifreeze in your car doesn't freeze at 0 degrees Celsius, but it still does freeze at -10. So in really, really cold climates, we're not even, -20, -30, that's sufficient enough to freeze the water. If you're not starting your car every once in a while and heating it up a bit, freeze the antifreeze, I should say, in your vehicle. Now, -103, there you go, and -10 degrees Celsius. The last colligative property we have to talk about here is osmotic pressure. We've talked about vapor pressure, we've talked about boiling point, we've talked about freezing point. The last one is osmotic pressure. And all of these, remember, are colligative properties, meaning they depend on how much solute you're pouring in, not necessarily what the solute is. Okay, it's the intermolecular forces aren't as important as just the quantity that is sort of blocking the way of molecules getting to the vapor phase if it's vapor pressure, or here creating this concentration gradient. So osmotic pressure relies on osmosis. And what you see here is a semi-permeable membrane at the bottom of this U-shaped container, and this lets some small particles through but blocks larger particles. Your cell membrane in your cells function exactly like this semi-permeable membrane. So what happens is there's this natural flow of water, this osmosis that happens, and it always happens from low concentration, to high concentration. Okay? It's trying to reach this equilibrium, right? The water is going to move from where there's not a ton of solute to where there is much more solute, because the concentration of red particles here are very close together, okay? And that makes water angry. The red particles are very spaced apart, but water wants everything to be equal, so the net flow of water is to the left, the water level rises, the particles are now spaced equally compared to the right side, and overall there's this nice equilibrium in terms of the concentration, right? Before this image on the left, this is much higher in terms of concentration than the right. And so water moves in this direction to dilute that side. Okay, so the net movement of solvent molecules here, we're talking about water, that's the most common examples, but any solvent will operate in this respect. It'll move from this low concentration to high concentration across this semi-permeable membrane. Here with water, it's osmosis. With other solvents, you might see it called diffusion. Now, osmotic pressure is the property we care about here, and I'll show you why in an example in a second. But here, now that you raise this level of water a certain height, Well, there's a pressure that is induced, and I think the formula is the density of water times the height it rises times the gravitational constant. Don't quote me on that, but I think that's the pressure of the resulting, that's the formula for the resulting pressure differential now, the extra pressure that is created on the left side. Not important in terms of taking an exam in the classes I teach, but sort of a fun fact, depending on your definition of fun. In any case, this is an extra pressure that results because there's an extra column of water here that is, has a weight to it due to this force of gravity, and that is the osmotic pressure. Now, in this class, in chemistry, often this is not the formula you're as concerned about. You're concerned with an osmotic pressure formula that looks much like PV equals nRT rearranged, where this pi symbol right here is my osmotic pressure. So that's how we're going to quantify this thing. Briefly first, though, I want to show you an example here of what happens in your body if you drink deionized water. Okay, if you drink deionized water, your blood cells, right, which might look like this by comparison, have a lot of particles and solutes in them inside their cell membrane. But if you're drinking a lot of deionized water, there's not a lot of ions in the water. And so the water will rush through the cell membrane wall, pictured here, trying to dilute all the organelles and compounds and molecules that are in your cells. And that'll keep happening and keep happening and keep happening until your cells explode. Okay, so that's here. That would be a hypotonic solution if you were drinking like deionized water. Don't do it, not recommended. Okay, if you're drinking something way too filled with ions and way too concentrated, well, then the water moves out of your cells and they shrivel up. Also bad, not quite as deadly. Okay, normally these are pretty extreme situations, right? And usually you're drinking many fluids that are isotonic or nearly isotonic, which means, the concentrations inside and outside your cells are relatively equal. There's an equilibrium there, but it's still dynamic. There's still water that you're drinking going into the cells, and there's other water coming out. It's just these rates are equal and opposite, so there's no net flow in or out, so there's no net explosions or shriveling. Now, let's look at this quantitatively and figure out what is the osmotic pressure for a given set of moles of solute, volume, I'm considering, temperature, and a gas constant R. I still here is my Van Hoff factor, right, that we talked about with our previous two colligative properties. Okay, so essentially you have PV equals nRT rearranged, so you can memorize this pretty easily if you're familiar with PivNert, but you're also adding this Van Hoff factor here. Okay, sometimes you'll see it written like this, since moles of solute per volume of solution is indeed molarity. That's basically molarity right here. Now, the R usually is going to be 0.08206. It depends on these units here, of course, but this is the one I use most often because most pressures are going to be measured in atmospheres and most volumes in liters in the science that I do. The temperature here is going to be Kelvin, another great approved temperature scale, just like Celsius. But that's the units that we want, which means if you're using this formula, any of these formulas here, make sure your temperature is in Kelvin, right? Make sure this N is moles of solute, not solvent, not total, and make sure your V is in liters. Again, the I term here, I equals 2 for things like sodium chloride, I equals 1 for non-electrolytes like sucrose, and I could be maybe 4 for something like aluminum chloride that ionizes to 4 ions. Now, if two solutions separated by a membrane have the same osmotic pressure, no net osmosis occurs, right? There's no net change in water, although water will be exchanged. It'll be equal and opposite rates. And so again, you'll be in this sort of situation here. Now, let's try to use this formula to calculate something. And one of the things that's really, really cool is back in the day, not so much anymore, but back in the day, people would figure out the molecular weights of compounds from this type of device. Because if you take this U-shaped device and put a bunch of solute in one side, you can see how much water rushes to the other side and back calculate what the molecular weight of that solute had to be. And so many times before we had mass spectrometry, which is much more advanced now, of course, you could measure the molecular weight of this particle, right, by just throwing it in these U-shaped devices with water. And that's what we're going to do in this example problem. Osmotic pressure experiments can be used to determine molar mass. So maybe we take 21.5 milligrams of a mutated hemoglobin protein. It's a non-electrolyte. We put it in water at 5 degrees Celsius. We have a total 1.50 milliliter solution, and an osmotic pressure of 3.61 torr is formed. What is the molar mass of this mutated protein? Okay, it's not hemoglobin usually, but it's now mutated. And what is the molar mass of it? Okay, so feel free to pause the video here and work it out yourself. I'm going to proceed and solve it now. All right, this is osmotic pressure, pi. I want that in atmospheres. The Van Hoff factor, I. Well, this is a non-electrolyte. That means I equals 1. N, I want moles. V, I want liters. R, I can write in R, I suppose, 0.08206 liters atmospheres per mole Kelvin. Times T, temperature, but that should be in Kelvin. So now that I have the formula, I know what I need to use, I can go back and write in each of these things. The atmospheres, the pressure here, well, I read through, I'm told osmotic pressure 3.61. Okay, 3.61 torr. I know there's 760 torr in an atmosphere, so I divide by that amount to get this into atmospheres. Okay, I have to do the same thing, of course, for my volume. So this is my pressure here, and this should come out to be 0.00475 atmospheres. My volume in liters, of course, well, that volume is this 1.50 milliliters, so move the decimal 3 places, and you have 0.0015 liters. Temperature in Kelvin, I'm given temperature in Celsius, so I add 273.15, and the temperature is now 278.15 Kelvin. So I have V, I have T, I have pi, I have I. The only thing I don't have is N, but that's okay because I'm figuring out the molar mass, which is grams per moles, and I have the milligrams. Okay, so again, with these problems, it can get quite complicated. Write out the equation, plug in what you know, rewrite it out. So now I have this osmotic pressure right here. That is equal to I, 1, N over V. N I don't know, but V I do. Times R, 0.8206, liters atmosphere mole Kelvin, times Kelvin, 278.15. And look, now I have everything to where I can solve for N. And so that's what I go through and do. And just make sure your liters will cancel with liters, your Kelvin will cancel with Kelvin, your atmospheres will cancel with atmosphere when you divide both sides by it, and you'll be left with mole in the numerator. So all of this you should be able to do and rearrange and come up with the number of moles in the end here, and the value here for N that you get after doing all that should be 3.12 times 10 to the negative 7 moles. That seems tiny. Now, this is my value of N. I dissolved 21.5 milligrams. So if I want to know a molar mass, my molar mass here should be grams per mole, right? Dimensional analysis, unit fractions like this, grams divided by moles. So this suggests I should take this milligrams and put it in grams, 0.0215 grams, divided by 3.12 times 10 to the negative 7 moles. Okay, and this is how back in the day we would measure molar masses. divide all this out, you get a final answer here of, rounding off to 3 sig figs, since that's what I was given in the problem, 68,900 grams per mole. That is a honkin' molar mass, but it is a protein, so it should be quite large. So again, the final answer here should be 68,900 grams per mole, worked out from an osmotic pressure experiment, just like they did back in the day. So that'll do it for this lecture on colligative properties, where we covered vapor pressure, we covered freezing point depression and boiling point elevation, and finally osmotic pressure, understanding the concepts, but also putting them into these mathematical quantitative problems. Thanks for watching. That'll do it for this lecture. See you next time.